Well, welcome everyone to our bi-weekly, it's not called bi-weekly, every 2-week seminar series, SIAM Financial Math and Engineering virtual seminar series. It's a pleasure today to introduce Professor Rene Carmona. So Rene, we all know him very well, but nonetheless, I'm going to give a little intro to him. He's a Paul M. Wythes 55 Professor of Engineering and Finance at Princeton University in the Department of Operations Research and Financial Engineering. He's an associate member of the Department of Mathematics, director of graduate studies at the Benham Center for Finance, where he oversees the Masters in Finance program. Rene is a fellow of the Institute of Mathematical Statistics and of the Society for Industrial and Applied Mathematics. He's a founding chair, in fact, of this very SIAM activity group in financial math engineering. He's also a founding editor of the Electronic Journal Communications and Probability and a founding editor of the SIAM Journal on Financial Math, and is on editorial boards of numerous academic journals. He's published over 100 articles and 11 books in various topics ranging in probability, statistics, mathematical physics, signal analysis, and financial math. And of course, in finance, he's widely known for his varied contributions in commodity markets, stochastic interest rate modeling, microstructure, among many others. And more recently, in particular with Francois Delarue, he co-developed a probabilistic approach to mean field games, which culminated in a state-of-the-art 2-volume book, which is rather thick, just even 1 volume. And in January 2020 was a recipient of the AMS's Dube Prize. So without further ado, Rene, we'd love to hear your talk on contract theory and mean field games to inform epidemic models. Take it away.
Thank you so much for this kind introduction and for inviting me. As you know, I care deeply about this SIAG. So what I'm going to talk about today is contract theory. It's mostly material taken from 2 papers I wrote with a former student of mine, Pei-Ki Wang. And I will try to, for the first half of the talk, review what contract theory is and try to emphasize the new life that a specific contribution of Svitanic, Tuzi, and Posamai gave to this field, at least among the financial mathematician and the probabilist of this group. But I will concentrate for the second half of the contribution of these 2 papers on the slide because they deal with the finite state space case, which is extremely useful, I believe, when you are interested in computation. In fact, you know, I want to have a quote from Markov. I leave my phone next to me to check on the time, and I just got a call that I want to cruise, I'm sure. A quote from Marcus, which used to say, "Be wise, discretize." Okay, so I want to use that as an alibi to study discrete discrete space, not discrete time, for this presentation. The second reason why I decided to talk about this subject is that in the mid-spring, when I was revising the file and preparing the final file for the second paper, the paper for management science, the editor asked, please, you give an example of the control of the spread of a disease. Could you, at least in the introduction or in the section of this discussion, add something related your work to the pandemic that we are living through now? So that, you never say no to an editor when your paper is not published yet. So I did just that, and that gave me some ideas about how we could extend this model and possibly contribute to the understanding of this current pandemic. So this is the work in progress for with 2 postdoc and 1 PhD student. I may not have much time to discuss what we are doing or trying to do, but at least this is a motivation for the title. I am not pathetically trying to follow the fashion and the trend that so many people work on COVID now, but that was basically prompted by the editor. So what is moral hazard and contract theory? That's something that is, let me start my clock. So we're going to have to look at models where one individual, we're going to call that the principal, is going to design a contract to incentivize one or several agents to behave in a certain way. So this has a lot of application. And as I said a few minutes ago, for example, for the control of a flu outbreak, for example, you would have a regulator trying to design a regulation to control the spread of the disease. But in finance, of course, the traditional example of being different. But the terminology I'm going to use, and which will have to be clarified in the mathematical models, are agency problem, of course, contract theory, moral hazard, and asymmetric information, which basically carry the same meaning as far as the model that I'm going to discuss are concerned. So historically, economists have been early at contributing to this field, first for one period model, so static models, and the early paper of Neerles and Holmstrom are notable in that respect. And then later on, people started working on a dynamic model, whether in discrete time or in continuous time. And you'll see that the name of Sannikov will come back many times, because he has been spending his entire life, even though he's still very young, promoting the use of continuous time model in economics and finance. And for probabilist or financial mathematician interested in probabilistic model, you know, on the wake of the work of Sannikov, what teased our interest was the book of Svitanik and Zeng, where they reformulated most everything in terms of backward stochastic differential equation. And noteworthy comment is that Holmstrom and Hart, these economists, early contributors to the field, got the Nobel Prize in economics for this work on contract theory. What are the data for a typical model in contract theory? I repeat, we have the principal who is going to design a contract, and an agent who is going to look at the contract, at the terms of the contract, and decide whether or not he's interested in working for the principal. So the principal will assume, and of course, we assume in the model that the agent are rational. And what that means is that they're going to behave in such a way that their expected utility will be maximized. Okay, so that's the meaning of the rationality of the agent. But you know, there's still no dummy. You know, if the contract is not interesting, if the deal is not worth it, they may basically bail out and tell the principal, sorry, I'm not working in this condition. The important thing is that the principal doesn't observe the gory details of the everyday life of the agent. The principal sees basically the result of the work or lack thereof of the agent. Okay, and say this is justifying the terminology asymmetric information and the terminology moral hazard. Okay, so in continuous time, this was clearly highlighted by the first papers of Yuli Sannikov, and I repeat, in continuous time, and presenting the model using a stochastic differential equation, and then reducing this contract problem to a standard, a more or less standard optimal control problem. And so that was a breakthrough, except for the fact that many people have had difficulty understanding what that meant, including me. People with a limited IQ like me had a difficulty understanding what this was really about. It looked like a miracle, what I will call throughout the talk, Sannikov's trick. Okay, but this was clearly, masterfully identify and explain, at least to probabilists, in a paper by Yaksat Svitanik, Dylan Sabmai, and Nizar Tuzi. And what I'm going to do is piggyback on this formulation of Sannikov trick to present what is behind contract theory. But of course, the extension to the original theory, which I'm going to be interested in, is when you have one principle and many agents. And so the major assumption we're going to make is that when the principle deals with a large number of agents, is still going to assume that the agents are rational, namely that the agent, whether they compete or not, are maximizing their expected utility, is going to present one uniform contract to all the agents, and he's going to assume that the group, the field of agent is in a sense symmetric. The agents are statistically identical. In other words, they're going to make decision on the same basis. They're going to use the same strategy. And each individual agent, when the number of agents is large, is going to have a minimal impact on the result of the group. Okay, so that's what we're going to end up doing, a principle facing now a field of such agent. And so typically what the principle is going to do is going to design a contract and choose the terms, the covenants of this contract in such a way that the agents are going to settle in a Nash equilibrium. Even if they compete, even if they are selfishly optimizing their own utilities, the agent is going to make sure that the contract they are offering is leading the rational agent to settle in a Nash equilibrium. Okay, what is the asymmetric of information consequences in terms of the mathematical model we're building? Well, this moral hazard is going to force the formulation of the mean field game to be what we call the weak formulation. So this is a standard approach in control theory introduced a long time ago by Kurtz and Davis. However, in mean field game, this was more recently introduced by a student of mine, Dan Lecker, and myself. So what I'm going to review in the next 10 minutes is what was done first in continuous time and continuous space, and then what was done later on with discrete state space. Okay, and you know, as a joke to see how old fogies like me behave, you know, discussing this problem. I've been doing that forever with Nizar Tuzi. Each time we would bump into each other in a conference, we would sit down and for half an hour, we would discuss this exact model and say, okay, so we're gonna have to do it. And after half an hour, we were starting talking about something else, gossiping about John Doe and Walter Smith, and then we were forgetting about this problem. But young, bright people finally decided to tackle this problem. And the first people to work on this exact principle many agent problem were Eli Mastroianni, and actually Eli and Possamaya, the first paper, and then they added Mastroianni to write the paper that I'm going to review quickly. And as I said, for the discrete case, this was a paper with my former student Peki Wang. So I'm going to try to explain a little bit more precisely what the weak formulation means and how it does capture this idea of asymmetric information and moral hazard. And typically, I basically already explained all the bullet point in this slide. Typically, what we're going to want is that the output of the work of the agent is going to be modeled by a stochastic process, which is going to be living on the canonical space, and this stochastic process being absolutely independent of everything when I think of the stochastic process as a function of t and omega. It's not going to be affected by the behavior of the agent. What the agent are going to affect when they make decision to work or not work hard, or play hooky, what they're going to affect is the probability distribution of this process. And that's the weak formulation. And this is relevant for this type of model because the principal doesn't see, as I explained, the gory details of what the agents are doing minute by minute, but he feels the net result of this work of lack or lack thereof. In other words, he sees aggregates quantity, he sees expectation of the return produced by the work of the agent. So basically he sees the distribution, or at least statics computed from the distribution. So that's what we're going to model in this weak formulation. Okay. So in the continuous case, and I'm going to review that relatively quickly. The typical space is the canonical space, the space of continuous function. We're going to take the coordinate process and the Wiener measure on this space. So the measure P is going to be the Wiener measure, and the standard sigma field filtration generated by the coordinate process. And if we want to be fancy, we're going to assume that there is a volatility process sigma. In the notation, it could depend upon the path, but it doesn't really matter. But this volatility doesn't depend at all about the behavior of the agent. And so we have a solution for this stochastic differential equation here. And the process xt is going to be this process, which I mentioned is unique and completely independent of the behavior of the agent. So what are the agent doing? So they're going to affect the drift of an Ito process, and only the drift. So the volatility has been already taken care of. So we're going to assume that we have a function b, which is function possibly of time of the state or the past history of the state, and an action that each agent can take. Okay, and we're going to assume that to be bounded. So we can define the I forgot to mention that the volatility sigma will have to be bounded away from zero, so it's going to be invertible. And so we can define this change of measure, okay? And through Girsanoff theorem, the script E being the, as usual, the Doolean exponential. And so under this new measure, our process xt, the path didn't change. But if we look at this path under the measure P alpha associated to control is going to be a solution of a stochastic differential equation, which is the Ito process we would like the output of the effort alpha to be. Okay, so that's the basically the setup of the weak formulation. And now whether we look at a control problem or a gain problem, we can work with that. Typically, in the case of contract theory, the principal is going to offer a contract to the agent or the agents, and the contract is going to be is going to comprise a continuous stream of payments, R sub t, and a terminal payment, which we're going to know by xi of t. And the agent, given the contract, if they decide to work, if they find the contract is agreeable, they're going to work and try to maximize their expected utility, which is going to be the sum of a terminal utility, a running utility due to the stream of payment coming from the principal, and of course the cost incurred for working, for producing effort alpha t when the state of the system, which at this moment is the return produced by the work of the agent, is given by a cost function c, right? And so in this case, now this is the end of the description of the problem. What the principal is going to do is going to choose a contract R and C, is going to assume that the agents are going to take this contract. So if there is only one agent in the classical case, is going to assume that the agent is going to work for this contract and maximize this expected utility. So in the back of an envelope, he's going to compute what is the expected, what is going to be the optimal behavior of the agent, assuming that is rational, and he's going to choose the contract to maximize his or her return, his or her expected utility, given that the agent is going to choose this optimal contract. So it is typically nothing more, nothing less a Stackelberg game where the principal goes first, announce the terms of the contract, and the agent reacts to that and do this optimization. So it's a set of two control problems, one inside the other. What is changing when we have a field of agent, as I hinted at before? The only difference is that the contract offered by the principal is going to be regarded as a form of common environment to all the optimization of all the agent. And we're going to expect, and at least the principal is going to expect, that the agent reach a Nash equilibrium. And so the Stackelberg is going to be the principal first, choose his contract, assume that the agent reach a Nash equilibrium. On the back of this envelope, compute the characteristic of this Nash equilibrium, and still the principal, sorry, is going to choose the terms of the contract to maximize its expected return. The difference now is that the coefficient of the problem, the optimization of problem of the agent, now the drift depend upon the state, the action of the agent, and the field of the other agent included in the model, namely that would be captured by the empirical distribution of the state or the control or the control of the agent, and of course same thing for the cost. All right, I stop here just for a second to see if there are any question. I'm rushing, but Sebastian, are there questions?
Yeah, okay, we do have one question. So let me see, would you like to ask your question, Jalal? You can unmute yourself. I think I need to promote you one moment. Go ahead, you can unmute yourself.
I think he said that he has no mic.
Oh, he said he has no mic. Okay, so I'll read out the question. It says, can we say this is a mean field type game with common noise, where the common noise is decided by the principal? Perhaps principal and other agents may be viewed as major minors. Okay, I see at the end of the question it says, sorry, I have no mic.
Okay, so indeed, there is some common noise. However, in many economic application, and we can view contract theory as one of them, the common noise doesn't have always the structure we use in some of the writing, and in particular, I'm guilty of having done that in the book. In other words, probabilist or mathematical finance people, when they have a common noise, they take it additive. In other words, we have an equation which looks like a standard equation with an idiosyncratic noise, and we add something independent, but we add it. So that's the model that we consider with a common noise. Typically, in many economics applications, this is not the type of model which is natural. The common noise could be, in a very complicated way, correlated with the idiosyncratic noise, but have an independent component which may not be able to be separated so easily. For example, the common noise could be appearing in the volatility of some of the equations for the individual agent. So if we admit that common noise could come in many different ways, yes, indeed, we have an extra noise coming from the contract, for example, of the principle, which is some sort of random environment more than a common noise in the way we have been solving this model. Okay, so that's one thing. Also, you can think of major minor, but for major minor, not all the models of major minor player end up with a Nash. Some of the original models of major minor were looking for a Nash equilibrium between all the players. In other words, you think of one major and n minors, we're looking for a Nash equilibrium among the n+1 player. Here, that's not what we're doing. We're doing a Stackelberg. In other words, there is one player going first. Yes, maybe he's big, maybe he can be looked at as a major, and then a field of minor. So, they can be looked at minor because they're a little dude working for the big guy. But the type of equilibrium is not necessarily a Nash equilibrium between the two. We're looking for a Stackelberg, which is one optimization included in another optimization. So I hope this answers the question. The best way to answer the question is avoiding them and deflecting them, which is exactly what I did. All right. So
thanks for the comprehensive reply. So just let me interrupt quickly. So please do post your questions into the chat. And at the end, if you would like to ask them yourself, we'll unmute you and have you turn on your video. Okay, Renee, continue on.
Yes, and please, don't wait for the end to write your question. I'm more than willing to pose and entertain question. And as I said, I'll try to deflect most of them, but I will try to answer those that I can address. All right, so as I said, in the remaining time, I'm going to concentrate on the discrete state case because basically it had not been studied, even though, with Francois, we wrote 1,400 pages on what we thought was the state of the art in this problem, promoting what we call the probabilistic approach. We thought that the discrete state space problems were important enough to include them in the book. But we couldn't basically, or at least I could not, presumably Francois would have been able to do it if asked, but I could not write the probabilistic approach to discrete state space. So, we basically wrote whatever we could present for the discrete state space mean field game using AJB equation and Fokker-Planck equation, and not a stochastic differential equation, and not forward-backward stochastic differential equation, and not mean field stochastic differential equation or McKean-Blacksoff stochastic differential equation. And by the way, the control we were using, because we wanted to write an AJB equation, were a closed loop control, Markovian type of control. And I tried, and I wrote a few pages mumbling, trying to explain that it should be possible to use open loop control depending upon the past, but it was not clear and it was not satisfactory at all. Well, for this project, we realized that it was not that difficult, and a smart graduate student could basically help me see the light. So we're going to follow again the weak formulation because that's what we need. So we're going to have a common state process xt, and this process is going to be defined as the coordinate process on the canonical space, the canonical space being the space of Cadillac functions with the left limit at the end of the time horizon interval, okay? And the state space is going to be a finite set, and we're going to denote its element as E1, EM, and we're going to think of them as the unit vector in Rm, and that's not an innocent assumption. We're going to see that we're going to use that strongly. It's just a matter of coding, but we're going to use this representation of this finite state space. Okay, and as before, we need the equivalent of either the Wiener process or this Ito diffusion with a fixed volatility. So what we're going to take is a process which is a Markov chain, which from any state EI can jump to any other state EJ with the same probability. So typically, this is a continuous time Markov chain whose Q matrix is given by 1 everywhere except on the diagonal where you have the negative of the sum of the terms, namely minus and minus 1. Okay, so that's going our basic process, which we're going to try to change the distribution of. Okay, so the measure P, we're going to try to change it. Just 1 second. My laptop was about to run out of battery. So that's going to be the equivalent of the space. Now, we learned from a paper of Cohen and Elliott that we can write this as the solution of a stochastic differential equation driven by an Rm value martingale. And this martingale, of course, will have a lot of jumps. And this martingale is also characterized by its predictable quadratic process, which is given in an explicit form here. Remember, Q0 is this Q matrix of this basic process. Okay, so that's one thing. So now we can go ahead and try to do the same change of measure. Okay, and for that we're gonna use the simplex for the space of measure on the state space. So we're going to use the notation S for simplex, and we're going to use probability measure on the space of control, which is the space of action can simply be a subset of Euclidean space. And typically we're shooting for processes which could be Markov in case the controls are feedback. And if they're Markov, they will be identified through their Q matrix. And the Q matrix should be a function of the action taken by each individual player, the distribution of the states of all the other players, and the distribution possibly of the control of all the other players. So we're shooting for processes of this type, okay? And so we're gonna make an assumption that the Q matrix we're looking for, they should be a Q matrix, namely on the diagonal, you have the negative of the sum of the entry of the row. We're going to assume a Lipschitz property, which is a natural Lipschitz property with respect to the action and the measure involved. And then we're going to have a boundedness above and a boundedness below assumption. The boundedness above is kind of needed throughout. The boundedness below is very restrictive. Why is it restrictive? Because in most practical application, these Q matrices have a lot of zero, especially if you want to use a large state space with a lot of element M being very large, you're going to have a lot of zero. So this assumption will not be satisfied for this model, but what this assumption is used for in the paper is basically uniqueness. So if you have another way to get uniqueness of the Nash equilibria, for example, some Last-Young's monotonicity condition, when you look carefully at the cost function, you do not need this assumption. Or if you can get unicity another way, you will not need this assumption. We make it here for the case of definiteness. So what are the individual agent in this field of agent doing? Well, they choose a control process, which is going to be, as before, a predictable process alpha. They're going to assume that the other guys are choosing their action in such a way that the distribution of their action and the distribution of their states are given by these two flows of measure. And now we would like to set up an optimization problem for the individual agent. And what we do is exactly what we did and the other dudes have done in the continuous state space, namely we're going to use Virsanov. So we define the martingale, which is going to be the candidate to build the density through a Dolian exponential. We have to check, because of the jump, that the jumps are not smaller than -1. So in this particular case, if defined this way, this is pretty simple. And so once this condition is satisfied, we can use Virsanov theorem and define a measure Q, depending upon the control alpha chosen by a typical player and the distribution of the states and possibly the control of the other player. And in this way, through Virsanov theorem, under this measure, the state, but the process X didn't change, but under this measure satisfies basically what we want, namely a stochastic differential equation driven by a martingale. And when the controls are closed loop, this is a Markov process with the right Q matrix, namely the matrix Q used in the definition of the density. All right, so that's worked perfectly. So what I want to present before I run out of time is a simple model of epidemic containment, which we wrote in the paper, and for which the editor of Management Science asked us to connect with COVID. This model was built up 3 years ago, just because we wanted to have a model we could solve explicitly. Okay, so no need to go through numeric calculation and machine learning and neural network programs. We wanted to be able to solve it analytically all the way to the end. So we designed this model not knowing anything about COVID. So in terms of COVID, it may not be that interesting. However, I want to describe it because we're going to see what type of feature allow you to get to a fully complete analytic solution. Fortunately, in the case of COVID and the extension of the SIR model, which some people have used, I may give some references, and we are trying to use, these assumptions are not satisfied. Unfortunately, if you try to use SIR model, even if you put them on steroid and generalize dramatically, this assumption is not going to be satisfied. So what is this model? So we have one regulator. Think of for 3 months I was watching every morning the press conference of Mario Cuomo, the governor of the state of New York, and so you are Mario Cuomo and you try to control this insane epidemic you have in your state. Okay, so and let's imagine then Mario Cuomo as only two cities or two counties in New York State. Let's say the city of New York and the rest of the states. Call them A and B. And let's be very simplistic. We're going to have infected people and healthy people. So the state space of this model has 4 elements. You're in city A and you're infected. You're in city A and you're healthy. You're in city B and you're infected. You're in city B and you're healthy. Only 4 states. And we denote by pi the proportion of individual in each of the states. Okay, so how are we going to model the evolution of this population of individual agent? So we're going to assume that if you're healthy in city A and you get infected at a certain rate, which is an increasing function of the proportion of infected people in your city. Same thing if you're in CTB, if you're healthy in the other city or in the other county of the state, you're going to be infected with an increasing function of the proportion of the infected. So this is reminiscent of the SIR model, but this is not exactly what you see in SIR model. For recovery, same thing. In each city, you're going to have a function, theta plus A or theta plus B, basically telling you what is the rate at which you will recover. And this depends upon the proportion of people infected still in your own city. Notice that this function in application and the numeric, we take them linear, but the slope of this function may, for example, account for the quality of healthcare in one city versus another, okay? Or the density of population for the function theta minus in one city or in the rest of the state of New York. So this model, even though naive, can account for a certain number of features. And what we allowed, we didn't know anything about COVID, as I said, we're going to allow people to move from one place to another, either because, in the city, the bars and the nightclubs are closed, and, I see that in Buffalo, they're open, so I'm going to take my car drive and go to Buffalo to enjoy my life. So we're going to allow people to move from one county to another, while the only difference is that changing counties will not change your state, okay? But we're going to allow this, and basically the only control we use in this small model will be the intensity with which each individual is going to try to get out of where he is, okay? So typically, this is the Q matrix we want to use for this model. You can go from being infected in CTA to remaining in the city and being healthy, so recovering through this function, as I said before. And as I said, the rate at which you move from CTB to CTA is given as by the rate is proportional to your control, okay? So we're gonna use cost for the agent and cost for the regulator. The costs are not too enlightening for the agent, but I want to emphasize what the regulator, my buddy Como, is trying to do. He's trying to do two things. He's trying to make sure that the proportion of infected in both the city and the rest of the state are controlled. So he's going to pay a heavy price, an exponential price, if these proportions are high. But at the same time, he doesn't want everybody to leave the city and move to the countryside. So he's going to have possibly a penalty for the population at the end of the period to be different from the population at the beginning of the period. These are the only features that we included in this model. As I said, it's not very realistic for COVID, but at least that gives you a sense that what this type of model can do for you, okay? So with all these things, I'm gonna give you a couple of slides to present the general approach, which is basically Sannikov trick as explained to us by Svitanic, Posamai, and Tuzi, okay? And it is captured in a very simple formula. This is the definition of a Nash equilibrium, so I'm going to spare you that definition. But if I want to write down the optimal control problem faced by the principal, the principal, the regulator, has to minimize over the control that is going to choose, namely the regulation is going to impose on these people. And when this regulation is fixed, he's going to assume, and as I say on the back of the envelope, he's going to compute the Nash equilibrium in which the people from the city and from the rest of the state settle in. You have an extra quantity here, which is the participation constraint. And then under the measure associated to this choice of behavior alpha and distribution P, the individual agent minimize a type of function. Okay, so the trick of Sanikoff is that, well, we're going to write down what the solution of the mean field game is. Okay, we're going to compute the Hamiltonian, and we're going to see that the mean field games is solved if and only if we can solve a backward SDE, backward stochastic differential equation of the McKean-Vlasov type. So here is the backward SDE. It represents the value function along the trajectory. So that's typical in stochastic control and in game theory. And this is the McKean-Vlasov part, okay? Because this flow of measure has to be the flow of measure following the choice of behavior of the agent, and this is simply saying that the control minimize the Hamiltonian desirable, and this is simply explaining or restating the fact that we are in the weak formulation and with changing measure. So this is simply one BSD, or in the case of discrete state space, which characterize the Nash equilibrium. So typically what we're going to do is that we're going to look at the problem of the principal, that's the Sanikoff trick, and replace the search for the Nash equilibrium by the solution of this backward equation. I'm going to be 2 more minutes and I will stop. So that's what we're going to do. And in order to do that, we're going to notice that this terminal condition appearing in the optimization of the principal is very much related to the terminal condition of the solution of the BST. Think of U be the identity, and what we're going to do is we're going to substitute Y for this, and now we're going to be allowed to take Y in the forward time direction, okay? And now we're going to end up with a optimization problem for the principal, which involves only Z, which is the volatility of Y, and R, the control, the part of the contract, because of the form that we use in standard contract theory. We can separate the optimization over R, we can separate the optimization over R and end up with a stochastic control problem of the mean field type for the principal, where the control now has nothing to do with the original behavior of the agent, but it is this Z, this volatility of the solution of the backward equation, okay? And this is where things stops, okay? And so if you have a battery of a huge machine learning algorithm, you can try to solve this problem like we did with Matthew in 2 papers in the Annals of Probability and the SIAM Journal of Numerical Analysis. But if you want to have an analytic solution, you're going to have to do something else. You're going to have to assume much more. But what I wanted to do was to get to this point, which is basically Cvitanich, Posamite taught us, and show that the problem is clean, but it's extremely difficult. If you make some further assumption, and the assumption I insist are basically separating the contribution of the distribution and the control, both in the Q matrix here and in the cost. And in the cost, I don't have it. You may be able to replace this control using this complicated esoteric stochastic process Z by a control which is now going to be a purely deterministic control, which is interpreted as the expected value of the original control given the state, and you reduce the problem to a deterministic control problem on the simplex. So it's a control problem for the evolution of the distribution of the state and controlled by a deterministic control. So this can be solved very easily, analytically, sometime numerically. Anybody, including me, can write such a code for a problem. So one more minute. When you solve this problem, you can also pretend that the regulator is not there. So you solve only for the mean field game. This is basically the same equation. You solve for the mean field game by setting to 0 the coefficients of the regulator, the action of the regulator, and you can find the evolution of the rate of infection globally and in each city. If you look at this plot and that plot, the yellow curve should be the same, because what I changed from one to the other is basically I increase the cost to the regulator for having high number of infection in the city B. And if you do that, you see that the regulator takes action and reduces dramatically the infection in CGB. So depending on what the regulator cares about or is penalized for, the outcomes are very different. You can follow a few things, and as I pointed out, and then I will stop here, as I pointed out, in part of the cost to the regulator, we impose a term which penalizes the regulator if the population moves from one city to another. And so if there is not such a penalty, when this coefficient sigma p is 0, you see that under the planning, in the presence of the regulator, well, the infection rate is in the city A. Sorry, that's the population in city A increased dramatically. But if you do not want this to happen and you want the population to be stable, you increase this coefficient, and you see that now the population in the city A is trying to get to its initial value. So again, these are very naive model. As I said, they were built before we had any idea what COVID was, but as an application of contract theory, in particular as an application with a discrete state space, you can easily tackle a certain number of models, not all. You can tackle some definitely numerically after using Sannikov trick and ending up with a highly complicated optimal control problem of the McKean-Vassov type, which you can solve numerically, if you have enough computing power. But if you can manage if you can accept some simplification in your model, in this particular case, these are the separation of the contribution to the Q matrix and to the cost. You can also go all the way and find explicit solution. I will stop here. Thank you.
Okay, great. Thank you, Renee, for a very interesting and thorough talk. We do have some time for questions for the formal part. And I just want to remind everyone to stay after the formal part of the questions. We'll stop the recording and you can hang around for more informal Q&A and chats. So up first, we have a question by Qi Feng. Qi, would you like to ask the question yourself? You can unmute and turn on your video.
Okay, hi, this is Qi. So my question is, in the intensity matrix Q, is that possible to allow Q not being only constant, but maybe they depend on the process itself?
Depending on what? I didn't get.
Depend on the process, like Q of X S maybe.
So in the particular model, in the particular simple model here, sorry, where did I put it? Here we go. So there is no direct dependence upon the state except through the population. So in other words, it depends not on individual state, but the proportion of people infected in city A, infected in city B, etc. as I said, this is a simple model. If you want, and what we're working out now include something which is more SRR-like, indeed, you can include the individual state, and you need to, but in particular, even in this model, the optimal control is going to be an expected control, given that X equal E1 or E2. So the optimal control is going to be a function of the state. It's going to be a feedback control in this model, even if the Q matrix doesn't depend. But of course, you can write the Q matrix you want, and you can put dependence upon X. This approach leading to the optimal control of McKean-Vassoff equation basically is oblivious to that fact. Afterwards, when you want to simplify this control problem, then you have some difficulty. If one that I see immediately is that to solve the mean field problem of the agent, we write down a Hamiltonian and we maximize or minimize the Hamiltonian. If you write that in terms of AGB equation, this is the same thing. You're going to have a supremum over the control. And that quantity will definitely depend upon X. It will depend upon the adjoint variable. And so if you can manage this dependence, you will be able to go all the way through. There is no obstruction to do it. It was a very simple model that we wanted to solve here explicitly. But there's no, actually in the theoretical part, the Q matrix depends upon X. It's only in this particular model, which we wanted to solve all the way to the end analytically, that it doesn't. Did I answer the question?
Yeah, thank you.
Thank you.
Hey, we have another question from Birkin Yilmaz. I think you should be able to unmute and turn on your video if you wish.
Hi, so my question is, could it be at all possible to include the planner's decisions in the cost functions of the players, so that you would be solving for a joint equilibrium between the plan and the players themselves? Sort of like, if the term is appropriate, a game where the plan is a distinguished player somehow?
Several answers. I think even in this model, I think the cost of the individual agent players depend upon the behavior, or at least the choice of the control of the principal. The cost of players, for example, in the standard contract theory, it depends upon the contract. How much money I'm getting every day through these streams of payment, how much money I'm going to get at the end through the terminal payment. So these are the controls of the principal. What is slightly different here is that the principal doesn't have a state, okay? But he still has an optimization problem. But basically, you think of the state of the system, including players and principal, as the same for everybody. But the principal doesn't have his own private state, but he has control, and these controls enter the cost of the player. So in this particular case, whether it is this simple naive model of epidemics or the more general contract theory, there are two problems that you can tackle. The first, the Stackelberg problem, which is in a sense natural in contract theory, or you could look for a joint Nash equilibrium, whether or not the coefficients depends upon the control of each other or not. As long as the model for the agent is mean field, you can. This is a typical example of major minor, as we discussed previously. It is not the natural formulation of the problem in contract theory. Why would the regulator want to be in a Nash equilibrium with the minors, if you can justify this, that the problem is not a Stackelberg, it is a Nash equilibrium between the two, and you will find most likely a different outcome, different optimal control, an equilibrium control for the minors and the major. I believe that the first few papers written on major minor were very confusing. I'm not saying they were wrong, even though in one paper, in the first paper I wrote on the subject, I infer that some of them were, but definitely they were confusing between the difference between Stackelberg and Nash equilibrium between the whole entire population, including the major. So as I said, already in this model, the control, the choice of the principal enters the optimization of the minor. Clearly, in an epidemic, you need to know what the rules are, even though where I live, nobody cares, but you need to know what the rules are. And if you know the rules, you're gonna solve your optimization. But we can, as I said, we're working on a SIAM model on steroids, where we increase the number of states. So you could have individual who are not infected, but are very conservative, very prudent, like the old fogies like me. I'm not going out, I pay attention. Then you have people, again, they don't know whether or not they're infected, they've not been tested, but they are more socially involved, more active. So the control is going to be different, much higher in terms of social activity. You can think of Gen Z people, some millennium people going to Trump rallies. And so they will eventually have a higher probability to be infected. And then you can have people infected and hospitalized, people infected not knowing that they're infected. You could have recovered people, and you can model dead people. And in all of these states, you can also double them by saying, they're in city A or in city B. So you can boost the realistic feature or the lack of realistic feature of this model into something which is quite realistic. However, and I insist, if you want to follow the spirit of SIR model, you're going to run into one problem, which we didn't resolve completely, which is in this equation here. In other words, an individual agent, whatever his state is, the old fogies or the millennium, whatever, is going to try to socialize at a certain rate, and he's going to get infected according to the population of infected people. And so typically what you're going to get in your Q matrix is termed like this, which are typically product of one control and then a function of the distribution. And as I said, typically it is the expectation of the behavior of all the other one conditioned by the state. So for example, here, you look at the state of people who are infected, and you look at the average social behavior. And so the rate for common dude to be infected is going to depend upon this thing. So for this model, you cannot separate the contribution of the control to the contribution of the distribution already in the Q matrix. Even if you're willing to do that in the cost functions, both of minors and major, you cannot do that in the Q matrix. And these models are much more difficult to handle, because at least analytically, because of that. Analytically, they're more difficult to handle because of that. Sorry.
Thanks, Renee. I think we're going to have to. It's already 5 after. We're a bit over, but we can close the formal part of questions. But that doesn't mean leave. Stick around, and there are more questions in the chat, and so we can take them one after the other. But we'll stop the formal part, and if you'd like to stick around and be part of the informal conversation, let us know, and we'll promote you onto the panelists so that you can turn on your videos and mics. So with that, I guess thank you all for attending, and we'll have our next seminar in 2 weeks from today. I don't know, Agostino or Igor, would you like to announce anything about that upcoming seminar?
No, I think, yes, Igor already mentioned, yeah, we know the next talk will be delivered by Samuel Drapeau, and it will be exactly 2 Thursdays, in 2 Thursdays from now. So we all look forward to welcoming you yeah, at the next seminar. And of course, we want to promote interaction. And if you have any concerns or if you have any suggestions, please let us know, and we will try to accommodate you to the best possible extent. Yeah.
Great. Yeah, thanks. And also in the alternating weeks, of course, there's also the bachelor